Our standard free energy of formation, which is going to be very similar to our standard heat of formation. So delta HF, this is going to be delta GF. We're really going to define it in a similar manner though and use it in a similar way. I also am going to talk a little bit more about our standard Gibbs free energy change and actually start relating it to equilibrium. Before that though, I just kind of want to do just a quick review. There's been a lot of new terms in this chapter and a lot of changes and positives and negatives and equals to zeros and just a lot going on. So I feel the need to kind of summarize for you guys. So we've looked at a few terms. Our first one was our enthalpy change. So delta H is our enthalpy change. And our enthalpy change, or enthalpy in general, right, H, is the heat of our reaction. And remember that heat is a form of energy. So if it's a negative value, we're releasing energy, that's going to be a favorable process. If it's a positive value, we're gaining energy, that's going to be a disfavorable process. So a negative delta H, right, that tells us that my final is less than my initial, right? We lost heat energy. Remember, if something's generally lower in energy, it's more stable. So this is favored. If we were only looking at heat energy, we weren't considering randomness or anything else. If we were only looking at heat energy and nothing else, if it's a negative value for delta H, that is a favorable process. A positive value for delta H, this time it is gaining heat energy, right? My final is greater than my initial. That's how my change comes out to be positive. It gained heat energy. And then again, if we were only looking at heat energy, we were ignoring everything else, this would be disfavorable or unfavorable. Right? Things want to be lower in energy, not higher in energy. Again, there's other factors that are going to come into play, but if we were only looking at enthalpy, right, we were only looking at energy due to heat, then this would be true. We added entropy change, so delta S is our entropy change. Entropy was a measure of molecular or particle disorder, so it's a measure of disorder or randomness. Right, we talked about situations where randomness would increase. Right, if you go from a solid to a liquid, we're breaking connections, it's more disordered. Liquid to a gas, it's even more random, more disordered. If you increase the temperature, particles start moving faster. That creates more randomness, more chaos. If you have a small molecular compound compared to a larger one at the same temperature, the larger one is going to have more entropy because it has more bonds. Those bonds bend and stretch and vibrate, so they have more microstates, right? We said that entropy increases. Kind of the reason for that is that the disordered state is always more probable than the ordered state. If we had a positive change, right, that means it's gaining entropy. It's becoming more disordered, right? Our final entropy is greater than our initial. So it gains randomness or becomes more disordered. Maybe that's the better way to say it. And this tends to be favorable. Systems tend towards a state of larger disorder. I'm going to put an asterisk on this though, because remember, total entropy increases. So my system could actually decrease in entropy as long as the surroundings become even more disordered. So I'm going to come back to that. But in general, that tends to be favorable. Delta S becomes less disordered, more ordered. And then again, that means that my final actually lost entropy, right? It became less disordered. And then this tends to be unfavorable. So again, I'm sticking that asterisk on there. I mean, ideally, we should probably put asterisks up on enthalpy also, because I made a big deal that this is if only heat changes, right? Only. If all energy change are due only to heat, right? Because we know they're not, we know entropy plays a factor. So if we were to look at the two of those, we defined our new term, our free energy change, delta G. So this is our Gibbs free energy change. And our equation is we take our enthalpy change, we subtract our temperature multiplied by our entropy change. So we can have something that's disfavored in terms of enthalpy, favored in terms of entropy, and as long as that favored term, so it's at a high temperature, is greater than my disfavored enthalpy term, then overall it's still favored, right? It's the relative enthalpy to entropy and temperature. Temperature is a key factor here that's going to determine whether or not the reaction overall is favored or not, right? If our free energy change came out to be negative, it's spontaneous, right? It means it'll occur on its own without any external influence. Doesn't mean it's fast, right? It could take a million years and still be spontaneous. If it's positive, it means it's non-spontaneous. And then if it's equal to 0, it's at equilibrium. Remember that reactions always go spontaneously towards equilibrium, right? We talked about that back in probably chapter 13, where we had our equilibrium constant and then QC, our reaction quotient. And we compared QC to KC to see which direction it would proceed, right? Because it wants to get to equilibrium, that's its goal. So all spontaneous reactions go towards equilibrium. The opposite of a spontaneous is always a non-spontaneous, so at equilibrium, where those are occurring at the same rate, my free energy change is equal to 0. We also talked about our 3 laws of thermodynamics. I have reviewed those before. Remember, our first law tells us that our total energy remains constant, so my total energy change is 0, right? If it's constant, my final is equal to my initial, right? E total final is equal to E total initial. Oop, I didn't mean to do that. We had that our entropy change total for a spontaneous reaction is always greater than 0, which means our total, again, is, remember, is always equal to our surroundings. And you could write the same thing for, I'm just gonna run out of room, so that's why I'm moving it. You could write the same thing for energy, right? Total is always system, but for surroundings. So we could say that the energy of my system is equal to the negative energy of my surroundings, right? The two always have equal numbers, but opposite signs, right? If one gains, the other loses, and vice versa. For this one, I just know that when I add them together, they need to add to a number that's positive. And then, of course, we had equations for calculating those. We related our entropy change of our surroundings to the negative enthalpy change of my reaction divided by temperature. And then we could add that to delta S of my reaction, which we can calculate using standard molar entropies to get my total. The other thing we did, and this is where we got our Gibbs free energy equation from, right, this one up here, is we did a little manipulation of that equation. and we said that delta S total multiplied by negative of my temperature, and I actually want to put parentheses around that. Mathematically it doesn't matter, but I want to make a big deal about that sign, is equal to delta G. That's where that term is coming from, and we talked about how we got to that in a previous video. But for a spontaneous reaction, right, my entropy change is greater than 0, so it's positive, right? It's a positive value. So if this is a positive value for something that's spontaneous, this negative times that positive means that delta G is going to be negative. So if I go back up, negative delta G is spontaneous. So you can determine spontaneity based on both your value for delta G and your value for your total entropy change. They're just going to have opposite signs, right? To be spontaneous, I'm going to have a positive delta S total, a negative delta G. That's going to be spontaneous. Right? To be non-spontaneous, it would be a negative total entropy change, a positive Gibbs free energy change. That would be non-spontaneous. And then of course they're both equal to 0 if we're at equilibrium. So the new part we're going to talk about in this video is using standard free energies of formation. And I had mentioned at the beginning of the video that we're going to define this very similar to how we defined our standard heat of formation. It's going to be, in this case, the free energy change versus the enthalpy change for the formation of 1 mole of a substance in its standard state from its constituent elements in their standard states. So really just take delta H and swap it with delta G, and you have this definition. So my free energy, standard free energies of formation, and our symbol for it, delta G standard, so that not symbol, and then subscript F because it's for formation. And it's our free energy change. For the formation of 1 mole of a substance in its standard state from its constituent elements, so the elements that make it up, in their standard states. So if you were to make a substance from the elements that make it up, all of them in their substance standard states, what's the amount of energy that it would take? That sort of thing. Just like we had with our standard enthalpy, our standard heat of formation, right, delta H not F, if something already was in its most standard state, like oxygen, right, if I wanted to make oxygen, I would actually be making it from oxygen, right? Oxygen atoms make up O2, and the most stable form of oxygen atoms is O2. So this would have a delta G naught F of 0, right? It also had an enthalpy change of formation, right? My heat of formation, delta H naught F, also of 0. You get these values from the appendix, right? Appendix G. That was the column in the middle that we haven't been using until now. And then we can use them to calculate our standard free energy change for our reaction. So this is another way to calculate it. Instead of using our Gibbs free energy equation, delta H minus T delta S, we can calculate it using our free energies of formation. And it's going to be the same way. We're going to do our sum of our delta G naught F's for our products minus the sum for my reactants. And then that N in here, I do have to multiply it by the number of moles of each of those substances I have in my equation. So we'll do an example. We're going to calculate the free energy change for the following reaction. And we'll have 4 ammonia, and those are gases. I'm reacting it with 5 oxygen, also in their gas state, and I'm producing 4 nitrogen monoxides, also a gas, plus 6 water, also gases. And just like we had with our enthalpy changes and also our molar entropies, make sure you pay attention to the states of everything when you look them up, right? Water in its gas state is going to take a different amount of energy to create than water in its liquid state. So again, please be careful when looking these up. For this problem, I'm just going to give us a table. On tests and quizzes, you're going to want to have that appendix handy. So for nitrogen monoxide, 87.6 kilojoules per mole, so a positive value for that one. So forming NO from N2 and O2 would be non-spontaneous. For water, I have a negative 237.2 kilojoules per mole. For ammonia, we have a negative 16.5. And then oxygen, we already talked about this one. I'm forming oxygen from oxygen, so it's going to be 0. And then the math, same format that we've been doing before. So products minus reactants, make sure you multiply by the coefficients. So I have 4 nitrogen monoxides, so I'm going to take 4, multiply it by 87.6. I'm going to do the sum of my products, so I'm going to add 6 multiplied by my value for water, and then that gets all summed together, and then do the same thing for my reactants and subtract it from the product side. So 4 ammonia, so 4 multiplied by a negative 16.5, and then mathematically you could skip this step, but I'm just going to throw it in there. So you can see that it is the sum. If it wasn't 0, you would actually need that part. And then just like we were doing before, just be really, really careful with your signs when you plug these into your calculator. We're adding and subtracting, and there's positive values and negative values, and it's just really easy to goof that up. And I get that my free energy change is a negative 1006.8 kilojoules per mole. Because we're adding and subtracting for significant digits, it's the number of digits after the decimal point. So 1 after the decimal point, 1 after the decimal point, 1 at the decimal point. This number isn't really here. So 1 after the decimal point. So that is the correct number of significant digits. A lot of times folks will want to round to 3 because these have 3, but we're adding and subtracting, so I do have 5 digits in my answer because it's the number of digits after the decimal point for this one. And then is this a spontaneous reaction or a non-spontaneous reaction? What do you guys think? Yeah, hopefully you're saying spontaneous because I have a negative sign, right? Negative values for my Gibbs free energy change are spontaneous reactions. I want to do one more slightly different type of example in this problem. all using things that we've done before. So we're going to actually calculate delta H, so our enthalpy change, our entropy change, and our Gibbs free energy change for the following reaction. So I'll have 4 iron, and that's solid, plus 3 oxygen gas. We're just forming rust here, so rusty iron, iron 3 oxide, which is also solid. And then we're gonna answer some questions. Is it endothermic or exothermic? Is heat released or absorbed? Kind of redundant with the first question, but I want to know that you know what each of those mean. Does randomness increase or decrease? Is the reaction spontaneous, non-spontaneous, or at equilibrium? If not at equilibrium, at which temperature will it switch between spontaneous and non-spontaneous? And the way that we're going to do it is I'm actually going to use my heats of formation and my molar entropies to calculate delta H and delta S. So I'm going to give us those values, and then we're going to use our Gibbs free energy equation, delta G equals delta H minus T delta S, to calculate delta G. And we're going to do that at just 25 degrees Celsius. Let's actually add, let's do that, and I'm going to add to this question. Sorry, I'm making this up as I go. Is the reaction spontaneous, non-spontaneous, or at equilibrium? Let's actually add a temperature to this. Let's actually say at, I don't know, what should we do? 200 degrees Celsius. And then we'll base the second part of that question, what temperature will it switch, off of that temperature. Am I making sense? If I'm not, hopefully it will as we go through it. So some values I'll give us. You would look up these in that appendix again, but I will just give them to us. So we're gonna have our heats of formation. That's in kilojoules per mole. And we're gonna have our standard molar entropies, and that's in joules per mole Kelvin. So for iron, 0, right? Because I'm forming iron from iron, right? Fe is its most standard form, so I'd be forming Fe solid from Fe solid, so 0 for a change. Oxygen gas, also 0, right? I'm making O2 from O2. And then for iron 3 oxide, it is a negative 824.2 kilojoules per mole. Randomness, 27.3 joules per mole Kelvin, 205.2 joules per mole Kelvin, and then 87.40 joules per mole Kelvin. So using those, we're going to do the sum of products minus sum of reactants. to calculate delta H and delta S using the delta H F's and the S. Actually, this don't have the F. Sorry, I got carried away. Just S, standard molar entropies. I'm pretty sure I said it right, but there's no F there. Sorry, it's just the entropy of that substance. We're not forming it. There isn't a delta symbol. It's just how much entropy does that have. So how much disorder does it have? So our equation is up here. It's a lot of scrolling, but I have 2 iron 3 oxides. So let's do delta H first. 2 iron 3 oxides. That's my only product, so I don't need to add anything to it. And then I'm going to subtract 0 from it, right? Because I would take 4 multiplied by 0 and then add to that 3 multiplied by 0. So 0 plus 0 is 0, so I'm just subtracting 0. So for delta H, we get 2 multiplied by a negative 824.2. So a negative 1648.4. I actually, for this one for sig figs, I just have a multiplication. So I want the same number of sig figs that I started out with. No, sorry guys, 1 after the decimal point. I'm getting myself confused. So that 2 is an exact number, it doesn't count. So I'm just gonna do the 1648.4, sorry. Usually I'm pretty solid on sig figs. I hope so, right? So that's my value for delta H. Delta S, I still have 2 iron 3 oxides. I don't have any other products, so just that one. If I go back up, I have 4 iron, 3 oxygen. So 4 multiplied by my value for iron plus 3 multiplied by my value for oxygen. Add those guys together. So I'm grabbing my calculator here. Again, just be really careful with signs. I just typed in 250 instead of 205. I guess signs are the only thing you need to be careful for. And I got a negative 550.0, and then that's joules per mole Kelvin. So delta G is going to be equal to delta H minus T delta S. And I did say that the first time we're going to calculate it, we're just going to do it at 298 Kelvin, right? 25 degrees Celsius. Pretty sure that's what I said up here. Yeah, 25. So the two that we're going to do is just changing the temperature. My enthalpy change and my entropy change is going to be the same. It's just that temperature is going to be a different number. Do be careful now when I plug these in. This is where we can run into issues. This is kilojoules, this is joules. So what I'm going to do is I'm actually going to convert my entropy change from joules per mole Kelvin to kilojoules by just moving my decimal place over 3. So to the left 3 places when I plug it in. So just be careful for units. So negative 1648.4 kilojoules per mole minus 298 Kelvin multiplied by negative, don't forget the negative, 0.5500 kilojoules per mole Kelvin. again, just really be careful for signs. I need to stop talking while I type them in, otherwise I'll goof them up myself. So I got that my free energy change is a negative 1484.5 kilojoules per mole, and then that's at 25 degrees Celsius. I'm just going to write that down so when I do my other one I can keep track of what number is what. So back up. Endothermic or exothermic? So my value on my enthalpy change was negative. So exothermic. Does that mean that it's releasing heat or absorbing heat, right? If my value on this is a negative value, right, that means that my final is smaller than my initial. It lost heat energy, right? It gave heat energy off. Does randomness increase or decrease? My sign on my entropy change is negative, so my final entropy is less than my initial entropy, so it lost entropy. So randomness actually decreased. And then at 25 degrees Celsius, it is spontaneous because I have a negative value. We're going to do another part to the problem. This actually, we could say spontaneous at this temperature. And then we're just going to do another one just for practice. So my free energy change, negative 1648.4. And then I had said to do 200, do I remember that right? Yeah, 200 degrees Celsius. It does need to be in Kelvin, so I need to add 273 to that. So 473 Kelvin. And then negative 0.5500 kilojoules per mole. So typing that into my calculator. And I got a negative 1388 point. I guess I'm not paying attention to significant digits here. I'm going to write it all down. We'll go back and we'll look at them. 0.25 kilojoules per mole. Just kind of started writing down numbers. So sig figs for this one, we're multiplying and we're subtracting. So when I take the 473 and multiply it by the 0.5500, I actually want 3 significant digits in my answer. So this actually comes out to a negative 260. I actually still have it in my calculator. 0.15. But I only want, this is where it kind of gets tricky. I only want 3 significant digits, so I am just going to end it here. I know that 0 technically isn't significant because I would round off the 0.15, so if I was trying to express that number with 3 sig figs, I would need to put it in scientific notation because that 1 rounds the 0 to just a 0, right? It's not going to round up or anything. But I'm just going to remember the 3 sig figs. So then when I subtract it from my negative 1648.4, I'm doing digits after the decimal point. So this is actually just a negative 1388 kilojoules per mole. This one's at 200 degrees Celsius, and then spontaneous or not, it's still spontaneous. One more question. I know I made this one a long one. We're never going to get to the newer stuff. I just thought this was good practice. If we're not at equilibrium, which we're not, right, it's spontaneous, at which temperature will it switch between spontaneous and non-spontaneous? And that's where we're using that equation where we set our free energy change equal to 0, and then we end it up, right? If we do 0 is equal to delta H minus T delta S, right, because at equilibrium it's 0. So then rearrange to solve for T, we end up with my temperature is equal to delta H over delta S. So plugging those numbers in, negative 1648.4 kilojoules per mole, negative 0.5500 kilojoules per mole. Divide those guys out. And I get a negative 2,997 Kelvin. Sorry, that was moles Kelvin. So kilojoules per mole canceled each other, and I have 1 over Kelvin. That Kelvin's on the bottom of this. It's in the denominator there, so it becomes Kelvin. We could ask also, like, which temperature, like above or below that, does it become non-spontaneous? Oop, that negative isn't there. I'm on a roll of mistakes today, sorry guys. Negative divided by negative is a positive value, so a positive 2,997 Kelvin, which by the way is really hot, right? Boiling would be 373, this is 2,997, so that's a pretty dang big temperature. Kind of the way that I would reason through that is I know that at 2 temperatures below that, it's spontaneous, right? It's spontaneous at 473 Kelvin, right? 200 degrees Celsius. It's also spontaneous at 298 Kelvin. So below that temperature, we know it's spontaneous, which means above that temperature, it's non-spontaneous.